Picture this. You're sitting in your Cambridge IGCSE Physics exam, right? You've just finished a massive 6-mark practical investigation question on calculating density. You used the exact right formula, you crunched the numbers perfectly on your calculator, and you confidently write down your final answer. You move on feeling absolutely fantastic. But what if I told you that you just scored a literal 0 on that question? Yeah, 0. You fell into a massive, completely preventable trap that catches thousands of students every single year.
So, a student accurately measures the volume of a liquid, precisely records the mass, calculates the density as 8.924, and loses all the method marks. Why? Well, it's because of 2 fatal errors, combining early rounding and missing the final units. Writing 8.924 means absolutely nothing in physics without a unit like grams per cubic centimeter attached to it. Furthermore, if the raw data was only provided to, say, 2 significant figures, giving an answer to 4 significant figures demonstrates a total lack of understanding of uncertainty. This single, cold-open mistake is honestly the fastest way to drop an entire grade boundary in your 0625 exam. Welcome to this explainer, where we're going to fix exactly that.
Okay, let's dive into this. These crucial topics sit squarely within sections 1.1 to 1.6 of the broader Cambridge syllabus. We're talking numbers and units, measuring length and time, all the way through volume, mass, and density. Now, you might be tempted to think this foundational section is just a brief introductory chapter you can skim over. Please don't. It is the absolute bedrock of every single practical question you will face. If you don't master the specific rules for measuring and recording uncertainties right here, those mistakes will just bleed into your forces, thermal effects, and electricity answers later on.
Here is the hard truth, guys. Ordinary revision fails. It just does. Most students spend hours upon hours memorizing that density equals mass divided by volume. But knowing the equation isn't enough to survive practical investigation questions. The examiner isn't just testing your math skills, they're testing your scientific method. They want to see what we call exam-safe wording. They need to see that you actually understand variables, safety, reliability, and accuracy. If you only memorize formulas, you are literally leaving more than half the marks on the table.
Let me fire off some rapid-fire examiner warnings. These are the specific sneaky traps that catch even the most prepared Cambridge students. Missing final units, rounding numbers in the middle of a multi-step calculation instead of waiting until the very end, offering vague explanations when you're evaluating an experiment, messing up the scaling on graph axes, suggesting super weak practical improvements, confusing your independent and dependent variables, a classic, or writing conclusions that just aren't supported by your own data. Any single one of these will cost you, so how do we avoid them entirely?
So, the crucial point is replacing all that guesswork with a systematic approach. To turn abstract practical knowledge into a concrete, reproducible answering method, you need to use this 4-step high-mark answer framework. First, state the concept. What's the physical principle at play here? Second, provide the evidence or data. Pull specific numbers directly from the experiment. Third, apply scientific reasoning. Connect that data back to the concept. And finally, use exact examiner wording to lock in the mark. Don't just casually say what happened. Describe it using the precise terminology the mark scheme actually demands.
In a moment, I'll show you the examiner clue that changes the answer completely. But first, you need the framework that makes that clue obvious. Let's test this right now. I want you to pause and predict. If an exam question asks you how to properly record data for a pendulum's time period to ensure accuracy and reliability, what do you write? Think about the apparatus features. Think about the variables. Are you timing just one single swing? How are you handling the uncertainty of human reaction time? Engage with this for a second before we reveal the definitive top-band approach.
Now, what's really interesting about this is how simple table design alone secures data analysis marks. Consider a flawed approach, writing units, like a little m for meters and s for seconds, next to every single number inside the body of a data table. That is a massive red flag to an examiner. Now compare that to a top-band approach. Variables and precise units are stated clearly in the header row only. The body contains pure, neatly formatted numbers to consistent decimal places. It also specifies time for 10 oscillations, rather than just a vague time. This proves you know exactly how to reduce percentage uncertainty.
And this brilliantly illustrates the difference in examiner wording. When you're asked for practical improvements, it's massive. A flawed answer just says, "Do it again carefully." I mean, that means nothing in physics. Carefully how? What does carefully even look like? The improved top-band answer is incredibly specific. Repeat the measurement 3 times and calculate a mean to identify anomalies. See the difference? This wording proves you understand the concepts of reliability and systematic error reduction. You aren't just doing it carefully, you are actively applying a rigorous scientific method.
Spot the error.
graph skills, and practical uncertainties. Let's move to and see how this builds when the method marks get heavily concentrated and things get a little more complex.
Imagine I am the examiner grading your paper right now, red pen in hand. Here's my exact checklist. First, your graph scale must occupy more than 50% of the provided grid. If all your data is bunched up in a tiny corner, you lose a mark. Simple as that. Second, both axes must be labeled with the physical quantity and its units separated by a /. Third, when you calculate a gradient, I need to see a large drawn triangle on the line of best fit, usually taking up at least half the length of the drawn line. Finally, you absolutely must visually identify any clear anomalies before you draw that line of best fit, ensuring your line represents the true trend, not some random outlier.
0. That is the exact number of marks you will be awarded if your final conclusion in an experiment is not strictly supported by the data provided on the page. Even if you write down a 100% true physics fact, say, stating that density increases as volume decreases for a constant mass, if the data table in the question showed anomalous results that contradicted that, and you ignored the data to write down textbook theory, you get 0. You must evaluate the evidence directly in front of you, period.
So before you even think about moving to the next question in your exam, you need to run through this final practical check. Ask yourself, are my final units included? Do my significant figures match the least precise raw data provided? Is my graph scale expansive and correctly labeled? And finally, did I address safety and reasonableness? For instance, if you calculate the length of a lab bench to be 3 kilometers, your answer's not reasonable. Stop, find your calculation error, and fix it.
But here is the ultimate trap. Let's say you applied our high-mark framework perfectly. Your units are flawless, your significant figures are spot on, and your graph is an absolute work of art. But you still lost the final crucial mark. Why? Because you misunderstood the hidden command word. Did the examiner ask you to describe, explain, or evaluate? Because if you describe when you were actually supposed to explain, all your beautiful data means nothing. We decode this exact hidden trap in our next explainer on command words that decide the mark band. It is absolutely mandatory viewing if you want to secure those top grades. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Ask yourself right now, do you truly know what your examiner is asking you to do? See you in the next one.